Let's see some examples of finding particular solutions, and in fact then general solutions, to non-homogeneous second-order linear differential equations. Of course, the examples we're going to use will involve solving second-order non-homogeneous linear constant coefficient differential equations. In other words, where our differential equations, the ones we'll solve, will be of the form ay double prime plus by prime plus cy equals some function g of t. Here's our first example. We have y double prime plus 4y prime plus 4y equals e to the t. Now, in order to find the general solution to this differential equation, we'll need two things. We'll need to know the general solution to the homogeneous differential equation, and we'll need to know one particular solution to this non-homogeneous differential equation. We'll see later why it's often a good idea to start by solving the homogeneous equation. So we'll solve y double prime plus 4y prime plus 4y equals 0. And we already know how to do this. The characteristic equation is r squared plus 4r plus 4 equals 0. That's the same as r plus 2 quantity squared equals 0, or r equals minus 2, and this is a repeated root. So we have solutions y1 equals e to the minus 2t, and y2 equals t e to the minus 2t to the homogeneous differential equation. And you can check those, and you should check that the Wronskian is non-zero, so these two solutions form a fundamental set of solutions to the homogeneous differential equation. Now, how are we going to find a particular solution to this non-homogeneous equation? Well, here's a great technique in differential equations. We just guess. And I would say guess and check, but we're going to modify that a little bit. I like to call this guess and force, meaning we're going to guess a solution and we're going to force it to work. Now, how can we do that? Well, we want the left side, when we plug in y of t, to end up being e to the t. Well, if y of t is just e to the t, y prime will be e to the t, y double prime will be e to the t. Everything on the left will involve e to the t. But of course, you'll see that the coefficient isn't right. If y is e to the t, I haven't even written anything down yet, then here you'll have 4e to the t, this will be 4e to the t, and this will be e to the t. So I'll end up with 9e to the t. So just e to the t alone won't work. But if we take a constant times e to the t, we let y of t be a constant, I'll call it a times e to the t, then just what I was saying without writing it down before, y prime will be again a e to the t, y double prime is a e to the t, and then y double prime plus 4y prime plus 4y will be this plus 4 of these plus 4 of these. It's easily seen to be 9a e to the t, and this must equal e to the t, this thing on the right. So it's very easy to do that. We'll choose a to be 1/9, and everything works. So this is what I mean by guess and force. You'll guess a solution with coefficients that haven't been determined yet, and then you'll force it to work. Of course, the formal name for this is the method of undetermined coefficients. So if we guess a solution of the correct form with undetermined coefficients, all we have to do is then plug things in and solve for the coefficient that works. So here, what is our conclusion? Our conclusion here is that y of t equals 1/9 e to the t is a solution to the non-homogeneous differential equation. And you should always remember to go back and check all of that. What is our general solution then? Our general solution is y of t equals c1 times y1, that's e to the minus 2t, plus c2 times y2, which is t e to the minus 2t, plus our particular solution, 1/9 e to the t. And remember here, c1 and c2 can be arbitrary real numbers. So we've completely solved that differential equation. Let's try it in this case. What if we want y double prime plus 5y prime plus 4y equal e to the 2t? Well, very quickly, if we solve the homogeneous, first we see that y1 equals e to the minus 4t and y2 equals e to the minus t are a fundamental set of solutions, or this pair is a fundamental set of solutions. So the general solution to the homogeneous version of this equation is the set of all real linear combinations of these two functions. Now, how can we get a particular solution? Again, we see if we have e to the 2t here on the right, if we put in a function which is just a constant times e to the 2t, y prime will also be a constant times e to the 2t, y double prime will similarly be so. And if we choose the constant correctly, we can make the left side match up with the right side. So we'll choose y of t to be a constant a times e to the 2t. Now we just have to be a little careful here. Y prime of t is 2a e to the 2t. Y double prime of t is then 4a e to the 2t, so that y double prime plus 5y prime plus 4y is what? We have 4a e to the 2t plus 5 times 2a e to the 2t, that's 10 more, so we have 14 total, plus another 4. We end up with 18a e to the 2t. So then this must equal e to the 2t. In other words, a has to equal 1/18. So y equals 1/18 e to the 2t is a solution to the non-homogeneous equation. What is our general solution then? It's just y of t equals c1 e to the minus 4t plus c2 e to the minus t. And then we have 1/18 e to the 2t. And again, remember c1 and c2 are arbitrary real numbers. Let's see a slightly different looking example. Here we have y double prime minus y is cosine t. Let's first look at the homogeneous equation. That would be y double prime minus y equals 0. Again, you could look at the characteristic equation, r squared minus 1 equals 0. R is plus or minus 1. So we have y1 equals e to the t, and y2 is e to the minus t, our fundamental set of solutions to the homogeneous equation. Now, what should we guess for a solution to this non-homogeneous equation? Well, here we have cosine t. If we guess y is a constant times cosine t, this will be a constant times cosine t. In general, if we had a y prime term, and that's why this isn't really that great an example, but I already have it here, so let's play with it. In general, if you have y prime, that would be a constant times sine t, and then y double prime would get us back to cosine t. So for a general second order linear constant coefficient differential equation where the term on the right looks like cosine t, we would want to choose our particular solution to be of the form a cosine t plus b sine t. Here you can see, because we don't have the y prime term, that just the cosine t term will work, but in general you'll need a sine term as well. Let's leave it in there and we'll see how that zeroes out. Y prime of t, of course, will be minus a sine t plus b cosine t. Y double prime will be minus a cosine t minus b sine t. So y double prime minus y will be this minus this. You'll have minus 2a cosine t minus 2b sine t, and this must equal cosine t. So how do we do that? We need to take a to be negative 1/2 and b to be 0. In other words, y of t must be exactly negative 1/2 cosine t. What's our general solution? It's just y of t is c1 times y1, that's e to the t, plus c2 times y2, that's e to the minus t. Then we have minus 1/2 cosine t. And you should check that this works. Again, here c1 and c2, I'll write it in this time, are any real numbers.